Okay, I'm glad to be here. My life's been a little crazy, like all of you, I'm sure, the last little while. I'm sorry some of that spilled over to here, and I'm doing. Thank you. All right, so this is a paper about trying to estimate the effect of time invariant state variables on the expected value function. And the motivation is the expected value function represents the average welfare of individuals.
Sometimes complaining works.
I'm sorry.
All right, so this is a joint, let me start over. This is a joint paper with Victor Chernozukov and Vera Semenova. It's about trying to estimate weighted average of the value function, okay, in high dimensional settings, and how to do that. And the motivation for that is that gives the optimal policy, right? The value of an optimal dynamic policy that individuals are following in terms of the value function, right? The expected value function. So it's an average welfare, average across individuals, and we know that's okay for, at least in some settings. So look at average welfare. If average welfare improves under some policy, then I don't know in this setting, but in the demand setting, there's always some way to redistribute things so that individual welfare, all individuals improve. Okay, so that's our interest in average welfare. Gives the value of an optimal policy. The things that we're going to look at is the value of an optimal policy by groups. Okay, so if you have a time invariant state variable that represents different groups of individuals, different types of individuals by observed type, you can look at the value of an optimal policy by group. It can be used to quantify the effects of changes in the distribution of the time invariant state variables like initial wealth. And so one of the things we're going to look at is the expected derivative of the value function with respect to the time invariant state variables. That's one of the things we look at. And actually, also, a third example is going to be kind of a policy analysis variable or average value function where you change the distribution, by some policy, you change the distribution of this time invariant variable, and we'll look at the effects of that too. Okay, so this paper is about the estimation of these objects via neural nets and other machine learners that allow for high dimensional state variables. Okay, so that introduces the kind of complications that come from the bias that is inherent in any machine learning method. That's bias comes from the regularization or the model selection that you do to enable good predictions in high dimensional settings. Okay, what we give are debiased machine learners of the weighted average, average derivative, and other objects, and that's that third example that I'll get to, that depend linearly on the value function. And these estimators turn out they're doubly robust, meaning that if you have the value function wrong, it actually is still consistent. Okay, wrong in the sense of the estimate is not the truth. Okay, it's still consistent, and we'll talk about that and why that happens. And then weighted average derivative and other objects. We'll talk about those. These estimators are doubly robust, as I said, and allow for a wide variety of estimators of per period returns. Okay. All right. So this again is the motivation in terms of why we do the debiasing. Okay. Neural nets and other machine learners give good predictions in high dimensional settings that are inherently biased, and that's just statistical bias. That's not bias in terms of other kinds of bias people think about sometimes in context of machine learning. That's just pure statistical bias we're talking about. The source of the bias is the regularization of model selection that controls the variance in order to get good out of sample predictions. Okay, so that's done in various ways for various machine learners. For lasso, it's done by penalization, L1 penalization, penalization by the sum of the absolute value of the coefficients. For neural nets, it's often done by including a penalty term that's proportional to the sum squares of the coefficients, okay, by L2 regularization. And it's also often in neural nets, we often regularize when we use them by averaging over estimates obtained by running a stochastic gradient descent, starting from different random starting values while stopping duration short of convergence. You go for epochs, right? For various choices of initial values, and then you average over the different epochs. And they, you know, generally in practice, you know, there's lots of parameters, a huge number, right? And you never really look for convergence in estimating neural nets that I know of anyway. Some of you are much more experienced, so feel free to correct me. But they're, you know, the computation procedure itself is a kind of regularization, and this is now acknowledged and mentioned in papers on neural nets. Okay, so these and other regularization methods make the neural nets and other machine learning methods biased. Okay. So this bias is a problem for estimating the expected value function, right? That's an average, okay? Averaging reduces variance, but it doesn't, you know, generally reduce bias. And so what happens, right? The bias passes through to the weighted average while taking the weighted average reduces variance. That's bad, right? So you tend to get the bias large relative to the standard deviation. And so when it comes to inference, confidence intervals about these things, they're very bad. In fact, we don't have a theoretical result for neural nets, but for lasso, the coverage using the usual you know, type of standard errors, the plug-in estimators have zero coverage asymptotically. You know, it's supposed to be 95%, and the limit is 0%. And the reason for that is the bias dominates the standard deviation asymptotically. So what do we do about this? A solution is name and orthogonal estimating equations where the value function estimator has no first order effect. And so we're just going to construct those for average value functions. And then another statistical thing, cross-fitting can also help reduce bias, and it does reduce variance in some cases. So we'll talk about that too. Okay. So that's what we're going to do. We're going to do this for, you know, a particular setting, which I'll get to in a minute. Now, as part of this debiasing, there's always an extra function that shows up. A debiasing function that you need. It shows up in the bias correction. And they generally depend on this function, which will denote by alpha naught. And it turns, you know, one of the things you can do, and this dates from, actually the first ideas about this kind of thing date from the statistics literature, a nice paper in JASA and 10 years ago, actually. The orthogonality can be used to actually estimate alpha naught. The fact that there's a first order effect of the value function on the estimator is 0. That only happens when you're at the right alpha naught. So by going in different directions away from your estimated value function, you can create estimating equations for alpha naught, okay? And then construct from that an estimator of alpha naught. Okay, so orthogonality implies estimating equations for alpha naught, and in some cases, objective functions for estimation of alpha naught. Okay, so here, there's no objective function as far as we know of. It's just all moment conditions. So you'll see the reasons for that. It's going to turn out to be a non-parametric IV type problem for estimating alpha, as well as for, we'll look at debiasing. That'll involve a non-parametric IV type setup. But we do give here, sort of automatic debias, automatic estimation of alpha naught for the weighted average value function. So we'll see how you can do that by solving a set of moment conditions. Okay. All right. Okay. So any questions about that so far? Okay. Yes.
Can you briefly explain why we cannot identify the moment condition necessary for alpha to identify alpha naught?
If you, in many cases, you can go through, and we're going to do that. Actually, we're going to do the work to compute and see what the formula is for alpha naught, right? And then you can use that. You can use that. That's fine. The automatic method is nice because, as you move across, our motivation for looking at that is it doesn't require anything more than the orthogonal moment function to actually construct an estimator of alpha, which is nice. That way you don't have to, every time you come up with a new problem, you don't have to actually, figure out how to estimate alpha naught. Like in the dynamic discrete choice model, where you use CCP, and you estimate it. You can figure out what the alpha naught is. There's a formula for it. It's quite complicated. And so it's nice to just be able to avoid that. Yeah, so that's the reason. But absolutely, you can do that. Okay, so let's look at what we are talking about it. What kind of a dynamic setting are we talking about where we have a value function and we're going to be interested in the expected value function? So we're going to consider a setting where x is a vector of state variables, okay, and xt, that's just a first order Markov process, time homogeneous, stationary Markov process, so it's an infinite horizon. These are infinite horizon optimization problems we're looking at. Their objects will depend on the expected value function, which we'll denote by v naught of x, and that's the expected discounted utility, money utility of optimal choices given a current state of x. Okay, so well known what that is. Now, the way we're going to formulate, or the way we do formulate this, is in terms of the per period expected reward function. Okay, so the value function will depend on that per period expected reward function, and so that, as usual, the per period expected reward function, or the value function, sorry, the conditional expectation of a present discounted value of given this current state, that will sum equals 0 to infinity of beta to the t, where that's the discount factor, times the expectation of the expected reward function in time t conditioned on the initial x being x. Okay, so that's what we're looking at. The beta here is a known discount factor, so we're just going to assume that's known through what we're doing. For example, okay, so like, what is this thing in dynamic discrete choice? It would be the expectation of the per period utility function, assuming optimal asymptotic and optimal choices. So you would take the conditional choice probabilities, and you would use those in the way pioneered by Hudson Miller to integrate out the choices, okay, over the choices to get a per period contribution to the value function, a per period contribution that depends only on X. Normally, we think of this when we write down these dynamic optimization problems, we think of this as, the per period contribution depends on actions, right? Depends on actions. And what we've done here is we've integrated out the actions. Okay, so that's what this per period is. There's well-known formulas for dynamic discrete choice and other interesting settings, and I'll come back to that. Okay, we'll come back to that. For now, we're just going to take this as known. Turns out that's interesting enough by itself. And then at the end, we'll talk about how you debias for estimation of this. Okay. We're gonna, so this is just, standard present discounted value, right? Expected present discounted value, right? All right, we're going to use this recursive characterization of the value function in terms of the per period expected returns, okay? And, you just rewrite this the right way, and you get v of x, the value function is equal to the per period, right? This is kind of a Bellman equation integrating out the actions, basically, right? So the value function in time x is the per period plus beta times the expected value of the value function in the next period. So that's what the plus means, conditional on the current x. Okay, so that's kind of the value. That's a Bellman equation of the actions have been integrated out. Okay. Okay, so we're interested in the effects. So we're going to look at the effects. So why, the state variables, many of them will be evolving over time. And so, the way that they evolve depends on actions. It's an important way, and they're endogenous, basically. So we're going to think about some regressors that you might think about some state variables as being exogenous. They're really initial conditions on the dynamic choice problem. Okay, so we have S, that's going to be the ones that vary over time, and then we're going to have K, which don't vary over time. And so what would that be? Well, that would be like initial wealth. Okay, you're thinking of a dynamic choice. It depends on initial wealth. You have some, as it were, some wealth variable that enters this decision. And we're going to look at the effect of changing K on the expected value. Okay, all right. So that's what we're going to be looking at. Okay, so we're going to be interested in the effect of the time invariant variables K on the weighted averages of the value function. So we'll give some examples of this. Weighted average of the value function and expected derivatives of the value function, derivatives with respect to K. And also we'll give an example of a policy type object. Okay, so weighted average of the value function, we're just think about that as the parameter of interest. That's going to be our delta naught, what it denotes. Expectation of some weight that depends on the state variables times the value function. Okay, and so it's just a way to, you can think of it as weighting different state variables differently for whatever reason, and we'll give some good reasons later. But for whatever reason, for now, in terms of looking at the thing,
Doesn't that require you to be assuming that you are starting at the ergodic distribution?
yes.
You haven't said that. That's a crucial assumption. Please say that.
Yeah, okay. Very good. Right. So special case is when K is discrete values, and you might think about it just represents types of observable types of individuals. Okay, and there, the simple, that should be a small k. You can think about a weight which is just an indicator function for that group, a particular group of individuals, and divide by the probability, proportion in this population of those groups. Okay, so that's an example of a weight. Okay, and what you would get then from this is the average value function averaged over individuals who are in a certain category. Okay, and okay, so that's we're going to take that to be it'll be unknown in general. We're going to ignore that for now. Just focus on a weighted estimated. All right, another example is the average derivative of the value function with respect to the time invariant variable. Think of the, how on average changing wealth affects the value of an optimal policy. Okay, this parameter quantifies the average change in the value function with a change in the time invariant continuous state variable like initial wealth.
At which level of initial wealth?
What?
At which level of initial wealth?
Averaging over all initial wealth. So that's an average derivative. It's kind of a way of averaging the wealth effect over.
Okay, at every different level of initial wealth, you will have quite a different value. But you're just saying, I'm going to.
I just want to know.
Okay.
If everybody became more wealthy.
Please be explicit.
Yeah. Thank you. Okay, so, right, so parameter quantifies the effect of a change in initial wealth, the average effect of a change in initial wealth on the value of following an optimal policy. Okay, so both these examples, 1 and 2, are special cases of a parameter which looks like this. You're going to take the value function, you're going to take some linear function of it, right? And then you're going to take the expectation over the observed data, which consists here of x, basically x, just x at the moment, but I'll just put w in here for all the data. W is some known function of a data observation, w, and that is linear and a possible value function. Okay, so both these examples are examples of such linear functions of the value function. Okay, in example 1, m is just w times v, and example 2 is the derivative of v with respect to k.
So you care more about which before you put in this.
You would. You could do a weighted, you absolutely could do a weighted average here if it depended on, you could weight it by, yes, absolutely.
And the natural thing is just to say that that's 1. Every utilitarian, Benthamite utilitarian would be, it's 1.
Thank you for the motivation. That's good. Yeah, absolutely. Okay. Oops, okay, that was backward. Yeah, forward. Yes, it was forward. Okay, so we're going to view the true value function as a solution to a conditional moment restriction. Non-parametric ID, in other words. So here, this, we can rewrite that recursive definition wherever it is, right? Here, we can rewrite this as a conditional moment restriction, right? Where you put in V, you just pull the conditioning outside, and you take the residual to be B0. Actually, you take the residual to be beta times B0 x plus minus B naught of x, and then plus the per period term. Okay, so that turns it into.
Moments do not do a very good job of capturing a lot of things in practical models.
What?
Moments do not do a good job of capturing the value practical things in a lot of practical models. The first moment, the second model, biostress led us down the primrose path and convincing us that moments are the only way to do things.
Sure, but it's kind of the value function has a special position in that we think of it, right? I mean, it's kind of although I don't know the dynamic.
Being unemployed is very different than being employed. And it's hard to capture that with just second, third, fourth, fifth moment. It's very hard to get that right.
Yeah.
Even if it's a value function, it's very hard to get that right.
Sure. Yeah, you might. Yeah. So this is money expected value, quite right. But,
No. This is consistent with constant relative risk conversion utility, right? Everything I've done so far, I think.
Yes.
Okay. So it's not money expected value necessarily. It's not money expected value necessarily.
Yes, that's
So
good.
there's no relative, you could have your reward function be a constant relative risk aversion utility function.
Yeah, that's fine.
So it's not money utility.
That's the primary case I was thinking about where, you know.
Well, but the other cases are super important.
I understand. Yeah, I understand. Okay, so this becomes then a conditional moment restriction of this form. Okay, so here's your residual, and this residual has conditional mean zero conditioned on X. And that's a non-parametric ID problem that's been worked on previously by Newey and Powell and by I and Chen, among others. So in this paper, we give and analyze debiased machine learners with such parameters using the local robust paper. That's what this is referring to here that was talked about yesterday and with the students and in the summer school. And for now, we assume that the per period utility is known, and we'll return later in the paper to consider the case where that's estimated.
So this worked great for a representative agent model, but doesn't work well at all for a heterogeneous agent model. Does not work well.
Let's talk about that afterwards, okay? Because
That's a vital point. It's a vital.
let's talk about it afterwards at this point, because I think I'll get to the econometrics here right quick.
Okay.
Yeah, okay, and then we can come back to that later. Okay, so we're going to look at a debiased machine learner based on a name and orthogonal moment function, which will identify the parameter of interest and have the property that there's zero first order effect of the non parametric function, which is the value function. So we're going to get to do the debiased machine learning, we're actually going to get an estimating equation where the value function has zero first order effect. Okay, so how does that work? Well, it works with a very nice choice of alpha. Okay. Okay, so as in this paper, this can be formed, this name and orthogonal moment function can be formed as the sum of an identifying moment function and the first step influence function. Okay, so here's the identifying moment function, right? Just m minus delta, that identifies delta. Obviously, you take the expectation of this and solve for delta, you get delta naught, right? And then the first step influence function here, all of these NPIV things were shown in this paper to have first step influence, which is some function of the conditioning variable, right? The instruments, right, times the residual, okay? The orthogonal moment function is then the sum of those two things. It looks like this, okay? And so this moment function has the property that changing V has no first order effect on this, on the expectation of this, and at the true alpha, and also changing alpha to true V has no effect on the expectation of it. Okay. Okay, so there's the orthogonal moment function. You can use this to construct a debiased machine learner of the thing you're interested in from estimators V hat of the value function and alpha hat of alpha 0. And we also do this using cross-fitting, where the orthogonal moment function is averaged over different observations and used to form V hat and alpha hat. So you partition the observation indices into L groups. V hat of L and alpha hat L, the estimators that are constructed using all observations not in IL. Then here's the debiased machine learner. You just plug in, you do this cross-fitting here, where you only use estimates here, which don't come from the observations you're averaging over, they come from all other observations. Okay, and you take the average over all the other observations of all the observations. Okay, and that's what the estimator looks like. Okay, an estimator of the asymptotic variance is very simple. This should be a square. Sorry, there's a square here, and it's very simple. It's just basically just the sample variance of this. It's just the sample variance of this over all the observations. So, okay, and the reason that works is because this is orthogonal, so you can ignore the estimation of V hat and alpha hat in this. Okay, so that's the debiased estimator of the thing we're interested in. That should, I apologize, that should be delta hat. Delta hat. Okay, that should be delta. Delta hat, that's the estimator. Okay, just you can use 5 groups. That works pretty well in Monte Carlos and empirical applications. Seems to give pretty stable answers.
It will not work well in a lot of heterogeneous agent model problems because there are discontinuities.
Let's come back to that. Okay. I look forward to talking with you about it. I think that would be good. Okay, so here's what it looks like in example 1. Example 1 is just the weighted average. You just all is changing in these 2 examples is the M, right? You're just plugging in that M there for example 1 and plugging in the M here for example 2. Okay, they do have very different alphas. Okay, and we'll get to that. So again, this is the one. Okay, so one feature of this is it's actually doubly robust. Okay, this is actually doubly robust. What does that mean? Okay, here's the name of the orthogonal moment function. Right here, it's linear in V. And so from this locally robust paper, we know that the moment function is doubly robust in V and alpha. Meaning that for all V and alpha, if you evaluate the wrong V, but the right alpha naught, you get the parameter of interest. And also, if you evaluate the right V naught, but the wrong alpha, you get the parameter of interest. Okay? So this alpha is doing a lot of work here. It means this moment function doesn't even depend on V, right? It's equal to 0 for all V. What did I do? Okay.
Upgrade.
I'm a Linux person. I have no idea.
Yes. Those are the consequences
We all
of
love
using
Microsoft.
Microsoft products.
Right.
Okay, so let's
Using
look.
Microsoft in your life.
Okay, so let's look at alpha naught. It's doing something fairly special, right? At the true alpha naught, the estimating equation doesn't depend on V, so it's doing something fairly special. Okay, so to get to alpha naught, we need to do one other thing. We need to represent this linear function of V as an expected product of some W. We have it explicitly. That W is explicitly in example 1. It's just the W you're interested in. In example 2, you integrate by parts to get the W as the derivative of the log of the conditional density of K given S, which is minus the derivative of the log of the conditional density of K given S. That's from the literature on average derivatives. This is well known in the literature on average derivatives. Okay, so now to characterize, we just use global robustness in V of X and stationarity to characterize what alpha naught has to be. Okay, so write it out. This is the expectation of the first part by this Rees representation right there. This is the second part, okay? And then just use stationarity. The expectation of the middle part here is just expectation of alpha X minus times delta X. Now what delta X, that represents just a change in the value function away from the truth. Okay, and this is just gotten, this equation is gotten by just substituting in the previous equation that said that the expectation of the orthogonal moment function is 0. Okay, so great. Okay, and then what do you have? Well, you have this condition, right? You have this condition when you do this time change on the middle term, right? And that's true for all delta X. The only way that can happen is if this thing has expectation given X equal to 0. Okay, that's the only way this can be 0 for all delta X. If this conditional expectation is not 0, you just take the conditional expectation of it and pick delta to be that, and then it would be not 0. Okay, so the conditional expectation of this given X is 0, and that characterizes alpha naught. Okay, there's the characterization right there. Okay, and the alpha naught that solves this is the backwards present discounted value of the W. Okay, so that's our alpha naught. And that's why, not knowing the value function, why the value function doesn't affect this moment condition is because at the right alpha naught is because this takes care of the work, the dynamic work, to get you back to the parameter of interest. It's the net present backward discounted value of this W. Okay. Okay, well, I want to look at that a little more actually, because it turns out that it leads to another representation of the parameter you're interested in terms of the per period utility. Okay, so if you look at, there's an important representation of this expected weighted value function, right? Okay, and to get to it, we're going to use the present discounted value relationship or the representation of the value function. Take the expectation of W of X times that, right? And then do iterative expectations. It's this. You change the time subscript, right? You go back, use stationary time subscript, you go back T periods here, you get this. And now you do iterative expectations again, and then pull the sum inside. And so what do you get? You get that in the end, the parameter of interest can also be written as the expectation of alpha naught times just the per period utility. So again, this alpha naught's doing the work of getting to the value function using the dynamic process. Okay, so it's being done right here, and you can get it in terms of just the expected utility of the one-time period. Okay, so it's a dual representation of the thing we're interested in terms of this alpha naught. Okay, so that has some useful features to it. Okay, so again, we're going to use this dual representation. It's very useful when W of X depends only on the time invariant K. All right, and so this is an important special case here, and I'll give another one in just a minute. I guess that's all I got anyway. Maybe take 2 minutes for the, okay. So, all right, so suppose that the weight depends just on K, then look at the formula for alpha naught. You do this, well, K is time invariant, so that's just K, right? This is a formula for the alpha naught. You look at, it's just K, conditional mean of WX given, WK given X, well, K is an element of X, so that's just WK. So in fact, it's just the present discounted value of WK, and that's just 1 over 1 minus beta WK. So in that case, where the weight depends only on K, and in fact, the delta naught you're interested in is just the alpha naught times delta X, and that just becomes 1 over 1 minus beta times WK times the per period utility. So the value, the dynamics disappears. It's what happens, that happens because the weight is time invariant. Okay, and how to estimate it? Well, there's a very simple estimator right there. If you know the weight, you can just estimate it like this. And then if this is estimated by machine learning in some way, you can debias that. Okay, so more generally, you need to estimate alpha naught. Here's a way to do that. Only using the M. You don't have to get the Reed's representer for M. Okay, so it's a way to estimate it using an approximation to alpha naught, which is a linear combination of some dictionary functions. Okay, so here's the third example. It's probably the most interesting one. Let pi k denote a PDF of K, the PDF of K, and consider an alternative PDF pi star of K that represents a policy shift. So you're going to do something to change the distribution of initial wealth. And you know what? You want to know what that effect of that is on average, the expected value function, right? So then delta naught, what that would be is you take the integral of the value function over the conditional distribution of X given K, and integrate it over this new density. That's that part, and then you're going to subtract off the expected value function. And you can rewrite that as the expectation of WK P of X, where your W is this. Okay, so it's the new density resulting from the policy, and divided by the true density of K and the data that you have, minus 1. Okay, so that's like Jim Stock suggested a policy shift in terms of in regression models, and looking at where the outcome you're interested in is actually the average value of the regression. Okay, and here, you know, this is the average value, right? And the effect of changing the distribution of the time invariant K. Okay, then by this dual characterization, it's just 1 over 1 minus beta times the expectation of WK, which is this WK now, times the per period utility, expected utility. And to estimate it, you just plug in this weight times whatever your estimate is of the per period utility, right? And then you can estimate that policy shift. This is an estimator of the effect on the average value function of changing the distribution of wealth, initial wealth. Okay, now this in general, I now add back the delta hat. Okay, in general, delta is going to be estimated always, you know, whether it's a dynamic discrete choice with a conditional choice probability estimate of the per period.
Dynamic discrete choice, the value functions are kind of bogus, right?
They're what?
Bogus, right?
Well, let's talk about that. Give me 1 more minute, okay? That's a larger discussion.
Yeah.
Okay, so what you do to get the debiased machine learning, again, it should be delta hat, is you just add the influence function for estimated influence function for this, okay? And that does it, that takes care of it. In high dimensional state settings, this will be a high dimensional estimate, and this will be biased. We don't have we want to do some things. We want to look at actual estimation of that. We want, more important than good applications. We still need mean square convergence rates for this alpha hat, and we need large sample theory that includes that estimation. But we know just from the locally robust paper that that's the general version, where you have a correction term or debias term for the presence of this gamma zeta hat. That just comes about by integrating over the true alpha naught. Okay, it'll be the influence function of this, and that'll be what you get here. And of course, to estimate this, you'll have to estimate alpha hat, but you can do that. Okay, and then we'll eventually, shortly, hopefully, have a large sample theory that includes that. Okay, that's all I have. Any other questions? Yes.
So it does seem like the setup with K here looks a little bit like a group indicator or something like that.
Like what?
A group indicator.
Yeah, that's one of the
examples. And could there be some issues with incidental parameter problems with K small, or is that kind of not an issue in this setup?
You could have, if there were a lot of these Ks. Sure, it turns it into a non-parametric thing. Actually, if there's an input number of Ks. Turns out debiasing is still useful in that setting. If what we want to do is we want to average over conditional on one state variable, right? We're going to plug in the value function. We're going to fix one state variable, and then we're going to average it, and that state variable is continuous. The exact same thing will produce a better estimate than any plug-in thing, right? Because it has this debiasing feature, and the exact same thing you'll need to do for a machine learning estimate of a value function. You still need to do it in order to get something that's asymptotically normal. The rate won't be n anymore, but it'll be slower. So papers on this, there's a paper with Victor Nahul and Econometrics journal about debiasing when you're looking at estimates of things at a point. And there's also this Solis Fregonis, Foster and Fregonis have a nice paper in one of the machine learning journals that won an award, or won the best paper award